You think you're sitting in a chair right now. You think your fingers are touching a screen or a mouse. You think the floor is holding you up. But here's the thing, you're not actually touching any of it. Not really. And I mean that literally. There's no contact happening at all. Now, I know what you're thinking. You're going to say, come on, I can feel the chair pushing back against me. I can feel the solid surface under my hand. But that feeling, that sensation you call touch, is actually something completely different from what you imagine it to be. It's one of the most beautiful tricks that nature plays on us. And once you understand what's really happening, you start to see the world in a completely different way. Let me start with something simple. What do you think solid matter is? Most people picture it like a brick wall, continuous stuff packed together with no gaps. But that picture is completely wrong. Completely wrong. Matter is mostly empty space. If you took all the actual matter in your body, all the stuff that has real substance to it, and you squeezed out all the empty space, you would be smaller than a grain of sand. Much smaller. The rest of you, all that volume you take up is just emptiness with some very tiny things flying around in it. So what are those tiny things? Well, you've got atoms. And atoms are made of a nucleus in the center, which is incredibly small, and then electrons that sort of exist in a cloud around that nucleus. Now, the nucleus is maybe 1/10,000th the size of the atom. Imagine the nucleus is a marble sitting in the middle of a football stadium. The electrons would be like little gnats flying around somewhere up in the bleachers. Everything in between is nothing, just empty space. That's what you're made of. That's what everything is made of. So when you push your hand down on a table, your hand atoms are getting close to the table atoms, but they never actually touch. The nuclei never crash into each other. The electrons never merge. What happens instead is that the electron clouds around your hand atoms and the electron clouds around the table atoms start to get very close to each other, and then something extraordinary happens. They start to repel. Now, why do they repel? This is where it gets really interesting. See, electrons are negatively charged, and like charges repel each other. You probably learned that in school. But that explanation, while correct, doesn't really tell you what's going on at the deepest level. The real story is much stranger and much more wonderful. The thing is, electrons don't behave like little balls orbiting around the nucleus. They're not like planets going around the sun. That picture, which you see in every science textbook, is wrong. Dead wrong. Electrons are quantum mechanical objects, and that means they don't have a definite position until you look at them. They exist in what we call a superposition of states. They're sort of smeared out in a cloud of probability. Now, when two atoms get close together, their electron clouds start to overlap. And here's where the magic happens. There's a rule in quantum mechanics called the Pauli exclusion principle. It says that no two electrons can be in exactly the same quantum state at the same time. They can't have the same position, the same spin, the same energy, all at once. It's a fundamental rule of nature, and it has no classical analogy. There's nothing in your everyday experience that would prepare you for this rule. It just is. So when your hand atoms try to get close to the table atoms, the electrons have to obey this rule. They can't occupy the same space. They have to stay separate. And the force that keeps them separate, the force you feel as solidity, as hardness, as resistance, that's not really a force in the usual sense. It's a consequence of this quantum mechanical rule. It's the universe enforcing the Pauli exclusion principle. But there's more to it than just exclusion. There's also the electromagnetic force. Remember, electrons are charged particles, and charged particles create electric fields around them. When the electron clouds get close, those fields interact. Negative repels negative. And this repulsion, this electromagnetic push, is what you actually feel when you think you're touching something. So the sensation of touch, that feeling of solidity, is really just electrons in your skin pushing against electrons in the object. It's an electromagnetic force acting across a tiny gap of empty space. You're not touching anything. You're hovering above it, separated by a distance that's incredibly small but absolutely real. Now let me give you a sense of scale here. The distance we're talking about, the gap between your hand and the table, is on the order of angstroms. An angstrom is 1/10,000,000,000th of a meter. That's so small that if you took a human hair, which is already pretty thin, and you divided its width by 1,000,000, you'd be in the right ballpark. So yes, the gap is tiny, but it's there. It's always there. And this is true for everything. When you walk, you're not actually stepping on the ground. The electrons in your shoes are repelling the electrons in the pavement, and you're floating on this electromagnetic cushion. When you sit, you're hovering above the chair. When you hold a cup of coffee, The cup is hovering just below your fingers. Everything you think of as contact is really repulsion. Everything you think of as solid is really forces in empty space. Now, you might ask, well, if everything is mostly empty space, why can't I just pass through a wall? Why can't my hand go right through the table? And the answer is that those forces are incredibly strong. The electromagnetic force is one of the strongest forces in nature. And the Pauli exclusion principle is absolute. It doesn't bend, it doesn't give. The electrons simply will not occupy the same space, and they will push back with as much force as necessary to prevent it. Think about it this way. When you try to push your hand through a table, you're trying to force trillions and trillions of electrons into the same space as trillions and trillions of other electrons. Each pair is pushing back. The total force is enormous. It's so strong that the only way to get through is to break the molecular bonds holding the table together. And that's not easy. That's why tables are solid, not because they're continuous matter, but because the forces holding them together are incredibly powerful. But here's something even stranger. The forces we're talking about, the electromagnetic forces and the quantum mechanical effects, they're not instantaneous. They travel at the speed of light. When your hand gets close to the table, the electric fields from your electrons have to propagate to the table's electrons, and the fields from the table's electrons have to propagate back to your hand. Now, this all happens so fast that you don't notice any delay. The speed of light is about 300,000 kilometers per second, so across a gap of a few angstroms, the time delay is utterly negligible. But in principle, it's there. So what you feel as the instantaneous sensation of touch is actually a back-and-forth exchange of electromagnetic information happening at the speed of light across a tiny gap. It's not contact, it's communication. The atoms in your hand are talking to the atoms in the table, and they're saying, stay back, don't come any closer. And that conversation, that exchange of force, is what creates the illusion of solidity. Now, I want to go a little deeper into this business about electrons and the Pauli exclusion principle, because it's really one of the most profound and strange things in all of physics. The exclusion principle isn't just a rule that electrons happen to follow. It's built into the very structure of quantum mechanics. It's related to the fact that electrons are fermions, which means they have a property called half-integer spin. Spin is a quantum property that has no real classical analog. It's not like the Earth spinning on its axis. It's something intrinsic to the particle, a kind of angular momentum that the particle just has, even when it's sitting still. And particles with half-integer spin, like electrons, have this weird property that when you exchange two of them, the wave function that describes them picks up a minus sign. That minus sign is what enforces the exclusion principle. If two electrons try to be in the same state, the wave function has to equal minus itself, which means it has to be zero. And if the wave function is zero, the probability of finding the electrons in that configuration is zero. It can't happen. So the solidity of matter, the reason you don't fall through the floor, the reason you can pick up a glass of water, all of that is ultimately a consequence of the spin statistics theorem in quantum mechanics. It's a consequence of the fact that electrons are fermions, and fermions obey the Pauli exclusion principle. Without that, matter as we know, it wouldn't exist. Atoms would collapse. Everything would be different. Now, there's another aspect to this that I find really fascinating. When you push on something, when you feel resistance, you're actually doing work against these forces. You're putting energy into the system. And where does that energy go? Well, some of it goes into deforming the material. If you push hard enough, you can actually change the shape of the object, compress it slightly, bend it. That deformation stores energy, like compressing a spring. But some of the energy also goes into heat. When atoms get pushed closer together and then spring back, they vibrate. And those vibrations, that jiggling motion of atoms, is what we call heat. So when you rub your hands together, you're not actually creating friction in the way you might imagine. You're forcing electron clouds to interact, and that interaction generates vibrations, which heat up the material. The warmth you feel is the kinetic energy of atoms jiggling around. And here's the really beautiful part. All of this complexity, all of these interactions, they emerge from just a few simple rules. You've got the laws of quantum mechanics, which tell you how electrons behave. You've got the electromagnetic force, which tells you how charged particles interact. And you've got the Pauli exclusion principle, which tells you that fermions can't be in the same state. From those three things, you get everything. You get chemistry, you get materials science, you get the sensation of touch, you get the entire macroscopic world. That's what I love about physics. You start with these very simple, very fundamental principles, and then you follow the logic, you do the math, and you discover that all of this richness, all of this complexity is already contained in those simple rules. You don't need to add anything extra. You don't need magic. You just need to understand the rules and follow them wherever they lead. Now let's talk about what happens when you really do get atoms to touch. I mean really touch, not just get close. Can that ever happen? Well, yes, under very special circumstances. If you take two nuclei and you slam them together with enough energy, you can overcome the electromagnetic repulsion and actually get them to merge. That's called nuclear fusion. It's what powers the sun. Inside the sun, hydrogen nuclei are colliding with such high energy that they overcome the repulsion and fuse together to form helium. And when they do, they release a tremendous amount of energy. But notice what it takes. It takes temperatures of millions of degrees. It takes enormous pressures. It takes conditions that are completely unlike anything you experience in everyday life. Under normal conditions, at normal temperatures, atoms never touch. They just push against each other from a distance. There's also something called electron capture, where an electron gets pulled into the nucleus and merges with a proton to form a neutron. But again, this only happens under very special conditions, usually in very dense matter or in certain types of radioactive decay. It's not something that happens when you're sitting in a chair or holding a pencil. So the bottom line is this: in all of your everyday experiences, in everything you see and touch and interact with, there is no real contact. Everything is mediated by forces acting across empty space. The solid world around you is an illusion created by electromagnetic fields and quantum mechanical principles. You are a cloud of probability hovering near other clouds of probability, and the forces between those clouds are what give rise to the sensation of solidity. And I think that's absolutely wonderful. I think it's one of the most beautiful things about the universe. The fact that something as simple and mundane as touching a table is actually a quantum mechanical phenomenon, a manifestation of deep principles that govern all of reality. That's extraordinary. It means that every moment, every interaction, every sensation is connected to the fundamental laws of nature. And here's another thing. Once you understand this, once you really internalize the fact that you're not touching anything, you start to see the world differently. You realize that the boundary between you and everything else is not as clear-cut as you thought. You're not a separate object sitting in space. You're a pattern of forces interacting with other patterns of forces. The distinction between you and the chair, between you and the air, between you and the ground, it's not a hard boundary. It's a gradient. It's a region where forces transition from one configuration to another. In fact, if you go down to the quantum level, things get even stranger. Because of something called quantum entanglement, particles that have interacted in the past remain connected in a very real sense, even when they're separated by large distances. So in some sense, you are entangled with everything you've ever touched, or rather everything you've ever almost touched. The universe is not made of separate objects. It's made of relationships, connections, interactions. Now, I don't want to get too philosophical here, but I do think there's something profound in this. The idea that solid matter is mostly empty space, that touch is an illusion, that everything is connected through quantum entanglement, these are not just abstract ideas. They're the actual reality of the world you live in. And I think that should change how you see things. It should make you more curious, more humble, more willing to question your assumptions about how the world works. Because here's the thing. Your intuition, your everyday experience, it's a guide, but it's not always a reliable guide. Evolution shaped your brain to help you survive in a world of medium-sized objects moving at medium speeds. It didn't shape your brain to understand atoms or quantum mechanics or relativity. So when you go down to the very small or the very fast or the very massive, your intuition breaks down. The world stops making sense in the way you expect it to. And that's okay. That's what science is for. Science is the tool we use to extend our understanding beyond the limits of our intuition. It's the method we use to figure out what's really going on, even when it contradicts our everyday experience. And the picture that emerges, the picture of a universe made of quantum fields and forces in empty space, is far stranger and far more interesting than anything we could have imagined. So the next time you sit down in a chair, or pick up a pen, or shake someone's hand, remember what's really happening. Remember that you're not touching anything. You're hovering. You're floating on a cushion of electromagnetic force, held up by the Pauli exclusion principle, experiencing the illusion of solidity created by the interactions of electron clouds, And remember that this illusion, this beautiful, convincing trick that nature plays on us, is actually a window into the deep structure of reality. That's what physics is all about. It's about looking past the surface, past the obvious, and seeing what's really there. It's about taking the world apart, piece by piece, until you understand how it works. And what you find when you do that is that the world is far more wonderful, far more strange, and far more beautiful than you ever imagined. You can't touch anything, but you can understand why, and that understanding is worth more than any sensation.